So in this lecture, we're going to speak about two tests for the divergence or convergence of infinite series. More specifically, we're looking at the integral test and the p-series test. So let's begin by first looking at the integral test, which is stated as a theorem. So if f is a positive, continuous, and decreasing function for all x greater than or equal to 1, such that a sub n is equal to f of n for every natural number, then the infinite series of a sub n and the improper integral from 1 to infinity for f of x either both diverge or both converge. So to see this, I suppose I'll give a brief argument for this. We will show that, we'll look at the partial sums. That's how we determine convergence of the infinite series. And we'll compare the partial sums to, not improper integrals, we will compare these partial sums to definite integrals that you'll see. So first, we're going to first partition the interval one through n into n minus 1 unit intervals. All that means is that we're taking 1 through n and partitioning this into n minus 1 intervals of length 1. And you'll see why we're doing that in a moment. So suppose that f satisfies being positive, continuous, and decreasing. So, so maybe I should say that. And let f be positive, continuous, and decreasing for all x greater than or equal to 1. So that means it's above the x-axis and it's maybe like that or something. Here's a graph of f of x. Y. And notice now that, for example, maybe I have different colors here. That if we assume further, we are assuming that a sub n is equal to f sub n for all naturals n. Right, so these are the integers here, right? And this height here, that height right there is f of 2. But we know that that equals a sub 2 because we're assuming this as well. And that this height here, right there, right? So f of 2 is right there, f of 3 is right there, f of 4 would be like right there, and so forth and so on, right? The reason why we split this interval into unit lengths is that the area here is 1 times f evaluated at 2, which is the same thing as a sub 2. So this area is a sub 2, this area is a sub 3, this area is a sub 4, so forth and so on. That area is a sub n. So if we look at the partial sums here, we notice that they're below the curve, right? So then what we can say is that then since Sn is equal to so what is Sn equal to? It's the nth partial sum. It's that plus that plus that, all of them, right? But here, f sub 1 is like not included here, right? But what is so what we can say is that this is equal to these sums, right? Minus f sub 1. So this will be the sum from n is equal to 2 to n, or I'll say I. From I is equal to 2 to n to f sub I, and then minus f sub 1. Okay. And all together, right? So that plus that plus that, all of that together would be the nth partial sum. But now we want to compare this to the area under the curve. So what this is going to say, if I rewrite this, is that so the nth partial sum is equal to this plus f at 1, and that's equal to the sum from n is equal to 2, oops, sorry, I is equal to 2 to n, that's sub I. And so, because again, we're concerned about the nth partial sum and how that relates to the integral here, which here we can clearly see that that and that and that and that all together, that's at most the integral from 1 to n of the function f of x dx. Right? That's at most that. Okay. What's more is that if we look at a different area, get above the integral. So how can we say maybe where's f1? F1 is right there. F2 is right here. And if we look at this yellow area, well, what is this? This is like F1, that's the height there. It's like F1 plus, and then this yellow area here is like F2. So that's F2 times 1, 2 plus that through Fn minus 1. So altogether, I should have rewrote this. Well, let me rewrite it better. So Sn plus f at 1 is equal to the sum from I is equal 2 to n f sub I, which is at most the integral from 1 to n f of x dx, which is at most the sum from I is equal 1 to n minus 1 of S of I. Okay, but now the way that we've set this up, right? This sum is so this is like how this is related to the nth partial sum here. And this is like the S of n minus 1 partial sum. You see that? And this is the sum of f sub I, but really these are like, this is equal to a sub I. And this is really a sub I because they equal for each of those natural numbers. And we chose it to have unit length on the x-axis. So when you make these rectangles, it's just the height of the rectangle, which corresponds precisely to these values. So now that we have this inequality, we see that, so if, so now, I need to erase that picture. So now the idea is just to take n to go to infinity. So using this, so maybe we can say like if 1 to infinity f of x dx equals L, say exists, right? It converges. Then we know that the limit of Sn plus f of 1 is at most L, right? Which means that in the limit, this is bounded above by L minus f of 1. Now, since f was decreasing, we know that the a sub n's are decreasing, right? Which means that the partial sums are decreasing. So S of n is bounded above, S of n is bounded below, and the partial sums are increasing, right? We're adding more and more and more because we're taking these positive rectangles, and so S of n is bounded above and increasing, monotone increasing. So S of n converges, right? By some previous theorem, bounded monotone sequences converge. This sequence is bounded from above and increasing, so it converges. So let's say by a previous theorem. If this integral, again, this is just taking the limit as n goes to infinity here, right? So if this diverges, then this goes to infinity, but this is always bigger than it. Then limit as n goes to infinity of this sum here. Right? If we just take the limit here and that goes to infinity, and that has to go to infinity as well. And what does that equal? That's the limit as n goes to infinity of s of n minus 1. So all of that has to diverge. So in both cases, really, I only proved one direction, but that's all we need for our purposes, that if that diverges, so does the infinite sum. If that converges, so does the infinite sum. And it's because of the way that we chose to partition this interval, and we observed that this is bounded above by the area under the curve, because it's positive, decreasing, continuous, and it's bounded above here, so the integral is bounded above by the Sn minus 1 partial sum. So if that blows up, then that blows up as well. So that's the proof. I wasn't planning on doing that, but I thought it was important to, every once in a while, show you the reasons for why these theorems are true. Okay, but what you probably are wondering about is how to use it. So let's look at an example. So maybe let's look at the infinite sum from n is equal 1 to infinity of maybe n over n squared plus 1. And the question is, so does this converge? Not even converge to what, but just does it converge? So let's apply the integral test to determine this. And in order to do that, you have to verify that it's positive, continuous, and decreasing for all x greater than or equal 1. So look at our solution here, we can say like f of x equal to x over x squared plus 1, which for my purposes, I'm going to rewrite like this. Okay, so clearly for all x greater than or equal to 1, this is positive. It is continuous. We're not going to get any division by 0 or anything funky like that. But is it decreasing? So in order to show that it's decreasing, we use the first derivative test and show that the derivative is going to be always less than 0 for all x greater than or equal to 1. So that's why I wrote this function that way, because you know I don't like this quotient rule. So then f prime of x is equal to this plus, now I'll take the derivative of the other side, so this will be minus 1 times x, and minus 2 up there, and then the derivative of the inside is 2x. So I just have a feeling I'm going to have to rewrite it like this now. And now this becomes minus 2x squared over x squared plus 1 all squared. So combining like terms, that's x squared plus 1 over x squared plus 1 squared minus 2x squared all over x squared plus 1 squared. And this becomes minus x squared plus 1 all over x squared plus 1 all squared. And we can clearly see the bottom is always positive So the denominator is always greater than 0, but for x greater than or equal to 1, the numerator is always less than 0. So then we conclude that f prime of x is always less than 0, which implies that f of x is decreasing. Decreasing for x greater than or equal to 1 because of this. Then if x is in the interval 0, 1, then it wouldn't necessarily be decreasing. So now we can apply the integral test. Which means we need to evaluate the improper integral of this on the interval 1, of this function on the interval 1 to infinity. So we look at 1 to infinity, x over x squared plus 1 dx. And we know that this is equal to limit as b tends towards infinity of the definite integral 1 to b x over x squared plus 1 dx. And using u substitution, if u is equal to x squared plus 1, then du is going to be equal to 2x dx, which means that a half of du is going to be x dx. So we can take that in front of the integram. And we'll have a half up there. We have x dx is du. The 1/2 came out, by the way. And that's all over u. So it's just whatever u du. So evaluating now this integral, we have 1/2 times the natural log of absolute value of u, which was x squared plus 1, minus, oh no. No, I was right. Let me fix this. Times natural log of u, which was x squared plus 1, divided from 1 to b. So we get the limit as b goes to infinity, 1/2 of natural log of absolute value x squared plus 1. Oh no, b squared plus 1. Minus 1/2 of natural log of 2. But 1 squared is 1, so 2. Okay. Now, so then in the limit, it's easy to see that this is going to go to infinity. So does this series converge? No. It diverges by the integral test. Okay, so now on to P series. And I'm only going to say like maybe 2 minutes worth of information about P series because it's one of the easiest tests that you have. So the theorem. So P series test. And all this states is that the sum from 1 to infinity of 1 over n to the power p converges for p greater than 1 and diverges for 0 less than p less than or equal to 1. Okay. That's really, it's a really simple test. I don't even think that, like, is there an example that would be? Yeah, so like, it's very simple. So like the harmonic series, 1 over n, diverges. Because here p is equal to 1. Whereas if we look at the square of the harmonic, like that, this converges. The T-series test is probably the easiest of all of the tests for convergence that we'll encounter. Okay, so from section 9.3, homework, suggested homework, I want you to look at 3 through 15, and then 33 through 36. Okay, and that will be it for this recording. Next time we will look at comparison tests.